Okay, next we have optical properties of semiconductor. Now, the optical properties of semiconductors are divided into two categories. One is electronic properties, electronic properties, and the other one is lattice properties. Now, electronic properties is clear from this name, involving the electronic state of solids, while lattice properties involves the vibration of lattice. They are related to the vibration of the lattice, and they are related to the electronic states. So here we will just consider only the electronic properties. Or the optical properties which revolve around these electronic properties, while we neglect these lattice properties. So the first optical property is the fundamental absorption. Process. Now, when we know that in a semiconductor we have a conduction band and we have a valence band. The gap between conduction band and valence band is called the energy gap, which is represented by Eg. Now, if I consider, let's suppose, intrinsic semiconductor, then the number of the valence band is completely filled with electron, while the conduction band is completely empty. Now, if light, let's suppose we have a semiconductor material. If light, a photon of energy E is equal to E of the photon is equal to h nu, where h is the Planck constant and nu is the frequency, falls on this semiconductor material, then these photons will be absorbed by these electrons. So the photon will be absorbed by this electron, and this photon now jumps from this valence band to the conduction band. So we have a hole here and we have an electron here. But these electrons absorb only those photons. This is the energy of the photon. These electrons absorb only those photons whose energy is greater than or equal to this energy gap Eg. Like if energy of photon is greater than or equal to in band gap, then we have this fundamental absorption process. Okay, just a minute. If we have a photon whose energy is greater than the band gap, this band gap Eg, then electron will jump from valence band to conduction band. We can say that if energy of the photon, which is h nu, is greater than the band gap Eg, then we have a transition of electron from conduction band to valence band to conduction band. The absorption of this photon by this electron, while it's moved from conduction band to valence band to conduction band is called fundamental absorption process. Here we have this factor, which is the energy of photon, and Eg is the band gap. We can, in other words, we can say that the frequency must be like the frequency of the incident photon from this equation. Okay, I will leave frequency on this side. Nu must be greater than or equal to Eg over H. We have like if the incident photon has a frequency which is greater than or equal to this value, then we have fundamental absorption process. Fundamental absorption. By fundamental absorption, we mean that the electron will absorb this photon whose frequency is nu, and electron will jump from valence band to the conduction band. Now, if nu is equal to this frequency of photon is equal to Eg over H, then in the conduction band we have a large number of energy states, and the valence band we have a large number of energy states. This is the band gap Eg. If the frequency is this much value, then only electron from the top of the valence band will jump to the bottom of the conduction band. Like only electrons lies on the top of the valence band will jump to the bottom of conduction band. This frequency I am denoting it by nu naught, and it's called absorption H. By absorption H means it's just absorption on the edges of the band structure. Like electron from the top of the valence band will jump to the bottom of the conduction band, while these electrons located below the top of the valence band does not absorb this energy, because this energy is smaller than this Eg plus some value is here. So now the transition process, like the absorption of photon, okay, like the absorption of photon and transition of electron from valence band to conduction band occurs only if total energy and momentum of the system remain conserved. This transition, like the transition of electron from valence band to conduction band, the transition occur only if energy is conserved, this is first, and the second one is momentum is conserved. Okay, what is mean by means of energy conservation? Energy is conserved. What is mean by energy is conserved? Like suppose we have an electron in the valence band. This electron has a certain energy which I represent by EI, initial energy of electron. Now a photon of energy h nu falls on this material. This electron whose initial energy is EI absorb this energy, so its total energy now become EI plus h nu, and it jumps to the conduction band here, and here the energy is final energy. So the final energy will be equal to the energy of the electron in the conduction band plus the absorbed energy from the photon, like EF is equal to EI plus h nu, where EF is final energy of electron, okay, in conduction band. This is initial energy of an electron in valence band, and this is absorbed photon energy. Absorbed photon energy, like the photon which is absorbed is the energy of that photon. If this condition satisfies, then we have a transition of electron from valence band to conduction band. And the other condition is that momentum is conserved. What it means is, like here we have a momentum of this electron has a momentum, this electron has a momentum, and this absorbed photon has also a momentum. So we can say that h bar kf is equal to h bar ki plus h bar q. Right, the momentum of photon in the conduction band will be equal to the momentum of electron in the conduction band will be equal to the momentum of photon in the valence band plus the momentum of absorbed photon. But here kf is the momentum of electron in the conduction band, and ki is the momentum of electron in the valence band, and q is the momentum of absorbed photon. But we know that in optical region, this is the wave vector, okay, wave vector. This total is momentum. This total. These are the wave vector of electron in conduction band. This is the wave vector of electron in valence band, and this is the wave vector of photon. While in optical region, Q is approximately equal to 0. It's negligibly small. So we can neglect this value here. So we left with h bar kf is equal to h bar ki. So this is another condition for the absorption. We can say that h bar cancel with h bar. So the momentum of electron in the conduction band is equal to the momentum of electron in the valence band. Then we have a transition from valence band to conduction band. Now this all discussion is about a direct band semiconductor. The above discussion is for direct band semiconductor. In a direct band semiconductor, like if we draw the band diagram, then we have on one side we have energy. Here we have energy. On the other side we have momentum. Okay, a wave vector K. So in a direct band semiconductor, the top of the valence band and the bottom of the conduction band lie at same momentum. Lie at the same momentum. So example of direct band semiconductor are gallium arsenide, indium arsenide, and we have many more examples also, etc. So since electrons jumps from the top of the bottom band to the bottom of the top of the valence band, this is the valence band, this is the conduction band. So electrons jump from the top, leave a hole here, and jumps to a conduction band. We have electrons here, but these electrons in the conduction band can't stay for longer time. So after some time they will jump back to the valence band and occupy the space of holes here. So this inverse jumping, like jumping of electrons from conduction band to the valence band, is called recombination. So this is all about direct band semiconductor. In the next video we will discuss the fundamental absorption process for indirect band semiconductor. Thank you.